Sounds good.
Welcome back, everyone. So now we'll have a talk by Scott Morrison, who's been using Lean for at least 2 years. He was already there when I started. I think about 3 years, Scott, is that right?
Something like that, yep.
Yeah. He's based in Canberra, Australia, and usually works on like topological quantum field theories and even register a domain with that abbreviation. And he wrote a marvelous category theory library. At least he started it off and wrote some really nice automation. And he will tell us something about that now.
Great, okay. Yeah, so the plan is to just show you a few bits and pieces of what exists in the category theory library, and also to tell you a little bit about this automation that Johan mentioned. So just to make sure that everyone is on the same page, this file is in the Lean for the Curious Mathematician repository. If you need to get that repository, you can get it there. And in particular, this file is in the source/demos/category theory file. If you've already got a copy of that repository, do just make sure that you run git pull before reading this, because I've been updating this all day today, and there are lots of changes. I'll come back and talk about the exercises at the end of the demo. Okay, so how are things set up? Well, categories are implemented as a type class, just like for rings and modules and Lie algebras and whatever else. So that is, when we want to talk about an arbitrary category, we just have to have some type C, and then we add a type class, category C, which adds the extra structure. Now, there's a bunch of peculiar notation for using categories in MATLib. The most important one is that there is a special notation for morphisms, which just allows us to write an arrow between x and y to represent the collection of morphisms from x to y. However, it's not the standard arrow that you're used to typing for functions. This one you instead type using /hom, and depending on your font, it'll look like a slightly skinnier version of the normal arrow. Okay, so x hom y will be the type of morphisms from x to y. To write the identity morphism, we use this funny 1, which can be typed as /b1. And then given morphisms f from x to y and g from y to z, we write composition in this slightly funny way. The symbol there is /gg. It's kind of meant to be an arrow indicating do one thing and then another. And you will notice that this is composition written backwards relative to the rest of the world. This was a quirky decision I made when things got started, and no one has yet made the pull request that swaps all the compositions around yet, so we're still stuck with this. Okay, so let's just see how the very basics work. Here's an example where I set up some objects and morphisms in a category, and I've got some silly little equation here where I compose some morphisms with some parentheses and identities inserted. And we use the axioms much like we would in a ring or a module or something. I can rewrite by category.idcomp. Let me just bring up the goal view here. That removes the id in the composition, and then I can rewrite by category.assoc, and I get the celebratory goals accomplished. But of course, all of the simple lemmas are set up properly, so that works just by simp as well. Okay, let's move one step up the hierarchy. Next, we need to talk about functors, and for that we need to have a second category around. So we use variables to introduce another type D and put a category structure on that. We write functors using this funny functor arrow. You can type that as just /functor, or even I think just /fun will do. And one thing to notice is that functors are fully bundled, just like we've seen for linear maps and ring homomorphisms and so on. The functor contains as a field the data of how it transforms objects, but also as a separate field, of course, how it transforms morphisms. So here's just a little example of how we use a functor. So here we declare f to be a functor from C to D, x an object of C, and we can see that we write f.map for transforming a morphism. So f.map of the identity morphism is, of course, just the identity on f.obj(x). So this is the object level part of the functor. And one of the axioms for a functor gives us that. And similarly, there's a corresponding rule for composition. Okay. What else do we need to know? To write the identity functor on some category, we have yet another 1 symbol. This is in some other font we found. And the functor composition operation is yet another funny arrow. This is now /GGG. But I promise that at this point, we've pretty much finished with the new notation we need to introduce to deal with categories. There's not going to be any new arrows to deal with natural transformations. Okay, so let's just, yeah.
Why do we need different notations? Can we just overload these notations for functions and also for morphisms? For example, we can have the same notation for
there's
functors.
a level of overriding that you can do, but there are some things that are built into Lean that you can't touch. And in particular, the built-in function arrow in Lean would just cause a nightmare to try and overload. So we don't go near that one. Okay.
How about the composition?
No, the circ symbol is also out of bounds, and things go badly wrong if you try and overload that notation. Yep.
How about just the composition for functors? Can we denote it the same way as composition for morphisms?
So, okay, let's just prove this this little fact. I just do it by some long sequence of rewrites using the laws for functors and the laws inside the category. There is some unfortunate fact that the identifier functor.mapid exists elsewhere in the library. Unfortunately, before I came along, we already had sort of type level functors. That is, things like list and option are functors in the sort of Haskell sense. And we never moved functor.mapid for those type level functors out of the root namespace. Anyway, we can fix that at some point. Okay. This stuff is all just boring, manipulating the laws in a category and the axioms for a functor. Let's get on to the slightly more interesting part. I just want to show you how to build a functor. So we need to specify 4 fields: the object level map, the morphism level map, and the 2 axioms. So here I'm going to do basically something to do with your nata. Given an object X, I'm going to give you the functor from C to type. So here you'll notice that Lean is automatically inferring the correct category instance for type, where the morphisms, of course, are just standard functions. So here I say that the map on objects is just the homs from X into my Y. The map on morphisms is composition. And I then give little proofs for that those things are actually functorial in the fairly obvious and boring ways. However, when we set up functors and natural transformations and so on,
Scott,
in MATLAB,
there is a question by Sophie Morel. Why is there a star after type?
Yeah, okay. So this star is saying that we're happy to talk about type in whichever universe you like. And I'll come back in a little bit to universe issues in the category theory library. But this is saying that we're making a sort of universe polymorphic definition. This can be type in any universe at all. Okay, so in the category theory library, the functoriality laws and the naturality conditions and so on are typically extremely easy and boring. And it's a real hassle if we have to prove them over and over again ourselves. And the initial reason for writing the category theory library, or getting started with it, was actually to test some ideas for automation to do that. So if you look down here at this next example, you see I've done exactly the same thing, except I've just entirely omitted the map_id and the map_comp field. And the reason I can do that is because if I go and jump to the definition of functor, which hopefully I can do from clicking on the arrow, I can see it's got functor has these 4 fields, but at the end of map_id and map_comp, there is this funny thing that you probably haven't seen before, .obviously. So this is something called an autoparameter, and it lets us specify a default tactic to try to apply to satisfy that field. And that's what's going on here. The map_id and map_comp fields are just being automatically synthesized for us by this tactic, obviously. You may have actually met obviously before. It's pretty much just a synonym for tidy, which some of you have used in other places. Okay. Tidy in particular uses simp amongst other things under the hood. So the more simple MS you add, the more powerful tidy becomes, and the less you have to prove, the more fields get automatically filled in. One thing that is helpful sometimes is that you can always query tidy to see what it is that it did. So here I've put those fields back in, but just written by tidy. And if I leave off the question mark, it just does its job. But if I put on a question mark, then I get a little trace message over here, which tells me what that tidy actually did. And sometimes that can be quite helpful for reconstructing easy proofs. Okay. So I think the talk tomorrow on differential geometry will give another example of tactics being used to synthesize fields automatically. And a fun thing I did yesterday, I went back to Floris's pointed map exercises from the structures talk and did a speed run of those exercises, taking advantage of some of these autoparam tricks. If you load up this file and click on the YouTube video, you can watch me speed run those exercises. Okay. On to the next level, we need to do natural transformations as well. Well, you might fear that I'm going to introduce yet another arrow for you, but of course, what we immediately do is take the collection of all functors from C to D and give that the structure of a category. And so after that, to specify some natural transformation between functors F and G, we just use the category theory arrow. And Lean automatically works out from that we must mean natural transformations. So you can really think, and we'll see more of this later, you can really think of this category theory arrow as a kind of polymorphic arrow, which doesn't need to just be functions, but can be whatever is the appropriate sort of morphism, and it gets sorted out under the hood for you. Okay, so here's I guess one thing to say, if alpha is a natural transformation, then you can access its components by writing alpha.appx. Okay, and that of course gives you a morphism from f.objects to g.objects, where this time the morphism arrow is back in the original category C. Okay, and here's a little calculation, just checking the naturality square follows from alpha.naturality. Okay, so those are the most basic objects in the category theory library. Before we go on and see some of the things you can do with it, I just want to talk a little bit more about Sophie's question about universes. So out in the real world, we know that there are both small categories and large categories. And when you're working in set theoretic foundations, there's some distinction about whether objects are sets or classes and so on. Now, the type theoretic version of that is about universes. And the distinction is really about whether objects and morphisms live in the same universe, and that's a small category, or whether the objects live in one universe higher up than where the morphisms live. If you just think about the category of all types, that's pretty obvious. The morphisms are just functions, which are still in whatever universe you started with, but the objects, of course, are all types, and that thing is one level higher up. Okay, now, the decision we made was rather than have a separate theory of small categories and large categories, what we would do is just allow the two universes for objects and morphisms to be completely unrelated. So the general setup to introduce a category is to introduce two universes, U and V, and then say that the objects are some type in universe U, and the category is parameterized by some universe V, which controls the universe level of the morphisms. Okay, so large category and small category then become special cases. So if E is something in type U+1, then large category E means a category where the morphisms are in universe U, while the objects are in universe U+1. We usually don't need to write the second argument, the second universe argument for category, because Lean infers that automatically from the carrier, the type we're working with, okay? And if E is in type U, then small category E just means category.u.u, both objects and morphisms live in. Okay, so while we write all of the sort of abstract nonsense parts of the library in terms of categories with two independent universes, in reality, we're never going to use that freedom. It's only small categories and large categories that will actually show up. And of course, all of the concrete categories like groups and rings and topological spaces that we'll talk about a little bit below, those are all large categories. And typically the indexing diagrams that you might use for limits or colimits will be small categories. Okay, but for now, let's forget all that and not worry about universe issues in the rest of this description. Okay, so as I just mentioned, we've set up quite a few concrete categories, although we haven't tried to be exhaustive at this point. So here's just a little example. I can say, let R and S be commutative rings, and let F be a morphism from R to S, and let x and y be terms of R, and then f of x times y is equal to f of x times f of y. And we can just prove that by simplifying. Now this is actually pretty neat. We're expressing things in a very succinct way here. First of all, to introduce a ring, we just wrote R:com ring, rather than having to separately introduce a type and a type class on it. Similarly, instead of having to use a special arrow for ring homomorphisms, the 2 plus times arrow, we're just using the polymorphic category theory arrow, and Lean is looking at the source and target and working out from those which arrow we mean. Okay, but this all comes basically for free. We've also set up a coercion from comring back to type. I mean, it's effectively the forgetful functor. But this means that whenever we see a comring, Lean is happy to treat it as a type, and that's what lets us write x:r. Here, R isn't a type, but Lean coerces it to a type, so we can still talk about elements in just the same way. And similarly, even though this f here is a morphism, it's automatically being coerced to a plain function when Lean sees it being applied to an argument. Okay, so that's nice and arguably should be taken more advantage of, but is not used a whole lot in the rest of the library at this point. Okay, let me just briefly say something about limits and colimits. So we've got sort of the whole story of all of the basic notions. So we define what the cone over some functor is. It's some sort of cone point and a whole lot of morphisms satisfying the usual laws. It's expressed as an actual transformation. If you have some cone, there's some structure is limit, asserting that that really is a limit cone. And then we also have a type class version of talking about limits. Has limit f is a type class specifying that there is a particular choice of limit cone for that functor f. And so then we can just write limit f to obtain the limit point and various other functions which obtain the various universal properties of that limit point. Okay, there's also machinery for all of the typical special shapes of limits, and similarly for the sort of the bilimits, things like zero objects and byproducts and things like that. Okay, I'm not going to talk in much detail about the internal working of all that limit and colimit stuff, but I will just show you a cute sort of application of it to do some constructions. So I'm going to work in the concrete category of topological spaces. So that's this top here. And basically all of the concrete categories have a nice constructor, which is always called of, which just takes a type. But if you look at the signature of top.of, it's something that takes a type and the corresponding type class, and all it does is it bundles those together to give us an object of top itself, a bundled topological space. Okay, so I define R as sort of the bundled version of the real numbers. I define I as this bundled version of the unit interval in R, and I define point as the bundled version of the 1-point topological space. And then I set up some continuous maps, the map from X to a point, the map from a point to the left end of an interval, and the map from point to the right end of an interval. All that I'm doing in these lines here is demonstrating that those maps really are continuous maps. And then I set up a cylinder. So here I say a cylinder over any topological space is another topological space. And here I use prod, although maybe I should have, for clarity, written limits.prod. It's a function that's in the category theory namespace, which goes away and checks that the category we're talking about has a notion of binary products, and if it does, then it spits out the binary product of the two topological spaces that we put in. Similarly, once we've got that cylinder, we can do something like define the continuous map from X into the top end of the cylinder by using sort of the universal property of the cylinder. To give a map into the cylinder, it suffices to give a map into each factor separately. So we map X to X by the identity, and we map X to the interval by collapsing X down to a point and then including that point is the left end of the interval. And similarly, we can define the map, including the x into the bottom of the cylinder. And then that gives us a cute way to construct the mapping cylinder in one line. We think about this little diagram. If we've got a morphism from x to y, well, we can map x to y. Or alternatively, we can include x into the top of the mapping cylinder. And if you think for a moment about how these things work, the mapping cylinder is exactly the push out of that diagram. And so when we write this line here, Lean goes away and checks that the category of topological spaces has all colimits. It finds that someone's built that, and so it knows how to construct the push out and returns a topological space to us. Now, it is worth admitting here that while these constructions look kind of slick, the definitional properties of this push out are fairly ghastly. I mean, you've sort of got no guarantees at all about how this object was constructed for you. And to work with this mapping cylinder that we built here, we really have to use the universal properties. It's not really possible to unfold this in any meaningful sense. We have to work through the universal properties to get anywhere at all. Okay, sometimes that's fine, or sometimes it's a bit of a pain. Okay, I don't want to go on for too long, so I'm just going to show you sort of one more thing. I think really the category theory library that's in Lean at the moment is mostly sort of abstract nonsense category theory, but I think we're finally getting to the point where we can do the sorts of mathematics that really intrinsically need, or at least want, category theory as their basic language. So I think algebraic geometry and homological algebra, quantum topology, things like that are sort of the groundwork is now laid to do all those sorts of mathematics. One way in which the category theory library, I hope, will be important is really to sort of achieve one sort of polymorphism. When we set up the theory of presheaves and spaces equipped with presheaves and so on, we don't want to separately work with sheaves of sets and sheaves of rings and so on. We would really like to do this in a way that lets us talk about sheaves in some arbitrary category, or maybe sheaves in some category with some extra structure, products, or whatever else we need in order to do the constructions we're doing. And well, yeah, we'll see how that goes. One thing that we've set up just recently is the very basics of homological algebra, and I think that people could get started soon on sort of defining extentor, doing exact functors, proving the salamander lemma, all this sort of stuff. But it's not there yet, but the groundwork is laid. Let me just do a little example of a homology calculation. So whatever, ignore some little setup here I'm doing here. What am I doing? So here I set up Z as the bundled version of the integers as an adcom group. Here I define multiplication by k as a group homomorphism from the integers to the integers. And now I'm just going to build a little cochain complex. So here I want the cochain complex that has the integers at every step, and half the maps are zeros, and half the maps are just multiplication by I if we're at the ith step. Okay, so I can set that up. I build some cochain complex. I tell it what the objects are. They're all just the integers. I tell it what D is. If I is even, I do multiplication by I, and also I do 0. I do a little calculation that verifies that D squared really is 0. And then I'm just going to do this little check on this statement here. I want to ask Lean if it knows what the graded cohomology in the category AB of this complex is. And it says, yes, I know what sort of thing that is. That's a graded object, graded by the integers in abelian groups. Okay, so at least graded homology was the right sort of thing. It was a functor from cochain complexes to graded objects. And we can actually do the calculations. These are not very efficient ones, but here, like I calculate that the cohomology group at 2 is 0, and modulo a little sorry that someone really should fill in just about quotient groups. Should be very easy. The cohomology group at 3 is Z12Z, and so on. Okay. Let me just point out a few odds and ends before I talk about the exercises. There's quite a bit more that I didn't cover that's in the category theory library. We have adjunctions and equivalences and monads. We have abelian categories, monoidal categories. And there are just some sort of pointers at the end that let you jump into the bits of those theories. There's some fact about right adjoints preserving limits that you can go and step through. We have the definition, at least, of an abelian category, although somewhat embarrassingly, we don't even have the fact that additive commutative groups are abelian. I don't think we have a single example, but if someone wants to go and fill in these sorries here, we're actually pretty close to having that. A fun exercise might be to finish doing that. Nearly all of it is there. You just need the fact that if you've got an injective map between abelian groups, it's the kernel of its co-kernel. We should have that in the group theory library, but not in the category theory
When
library.
you're done, please PR it to MathLib.
Yeah, exactly. This exercise is a good PR. Yep. You can check that modules over a commutative ring. Lean knows that forms a monodal category. And you can even check that it knows that the functor from complete separable uniform spaces back down to uniform spaces is a reflective functor. Maybe who cares, but it knows.
Oh no, we absolutely care about that. That we needed that in the perfectoid project. That was
an
important thing, right? That was how this came up.
Yeah, so here, I mean, the fact that this functor, this forgetful functor is reflective, does give you something nice. I mean, it means that if you know how to compute limits, for example, just products in uniform spaces, it tells you that you can compute them in complete separated uniform spaces in exactly the same way. And gives you for free that the product here is just taken by doing the product over there. Okay. Okay. Jumping back to the top to talk about exercises. There are exercises for this demo. They're in exercise sources /Thursday/afternoon. I think Patrick, for example, was worried that my exercises were not going to be very approachable. And he was worried about who was going to be able to help doing them. But I promise they're fine and they're fun. But just in case, I wrote lots of hints. So you can look in source/hints, Thursday afternoon category theory, where you will find quite extensive hints. Where are they? Hints. Here we go. Exercise 2 has hints 1 through 7, all separate files. So you can use those to walk through the exercises. And there are partial solutions in the solutions directory. Exercises 1 through 7 should be are worth doing. Exercises 8, 9, and 10 are mini projects, and you shouldn't. Well, yeah, don't really approach those thinking you're going to do them this afternoon. But if anyone wants to finish them off, they'd all make good pull requests. Okay, I will finish up there and let us see any questions and go to break rooms.
Yeah, thanks a lot, Scott.
Yeah, great, thanks.
So, are there any questions?
Yes. So I want to know if we can have the category of categories.
Yes, it's there.
I see. But then I'm just worrying, since we have two notations, one for morphism, another for functor, and there, does it cause some problem?
No, it doesn't cause any problem.
It's
Okay.
really like there are two notations for the same thing, so Lean sees right through.
Okay. And what's the reason we must have two separate notations here?
Like I told you, we can't override the built-in ones that Lean uses for functions.
No, I think
It's not a built-in one. It's the two you created. The one for morphism and another for functor.
Okay, because you're thinking about things at two different levels and conflating the levels. So of course, notation, yeah, there are different notations for the same things. I don't think this is very surprising.
also, of course, I mean, we have the category of categories, but it should actually be a two category, and we don't have that. So
That's true.
I mean, yeah, this would be a completely different direction.
Yeah, we do have monoidal categories, and it should be almost a syntactical change to improve those up to two categories, but no one's done that.
So I suggest we go into breakout rooms, and further questions can be asked to the tutors. So let's see, I'll recreate some rooms. Oh, and